The left graph we have is the position time graph, and we have a straight line. We said the other day that velocity is the slope of the line on a position time graph. So if we use the change in position divided by the change in time, we get a slope of 0.8 meters per second. What we're going to do now is we're going to take that information and we're going to move it so that we can graph it on the velocity time graph. So on the velocity time graph, we need to choose a scale that will allow us to use the full quadrants. So if we make each tick mark a tenth, then we can put our scale on the velocity time graph, and we can look to see that each second on the position time graph, our velocity is 0.8 meters, so that we can draw a line showing us the velocity for this 10-second time, and each second it's at 0.8 meters. Our velocity time graph shows a velocity of 0.8 meters per second. It's a nice straight line. It's a horizontal line. When we look at our two graphs, what we see for a position time graph is when we have a straight line on our position versus time graph. That means that on our velocity time graph, we have a horizontal line. Both of them indicate constant velocity of our object. If we look at a second graph, we have three straight lines now on our position time graph. First thing we want to do is identify the velocity of each of our segments. First segment, we have a velocity of 0 because it's a horizontal line. The position doesn't change. Position is at 3 meters, so for the first 3 seconds, it's sitting at 3 meters. The next segment, we have a velocity of 2 meters per second, and it goes for 2 meters per second from time equals 3 seconds until time equals 6 seconds. Our third segment, the slope is 1. It's 1 meter per second. But since it's a negative slope, we have to treat it a little bit differently. If you remember the definition of velocity, velocity is change in position over change in time. We define change in position as final position minus initial position over time. Looking at our graph, our final position is 5 meters. Our initial position for that segment is 9 meters. So final minus initial is 5 minus 9. Our time is 10 seconds for our final position. Our time for the initial position is 6 seconds. So we end up with negative 4 over 4. That's how we end up with a negative 1 meter per second. Remember that negative sign means we're going in the opposite direction compared to the direction we were going for seconds 3 through 6. To graph this on our velocity time graph now, we have 3 different velocities. We need to choose where our reference point, our origin, will be. Because we have a negative velocity as well as a positive velocity, we need to put 0 not at the bottom. Putting 0 at the middle works best. So now we need to identify what our intervals are on the vertical axis. If we make each interval 0.1 meters per second, we'll have an axis, vertical axis, that looks like this. Converting our position time graph to velocity time graph, our first 3 seconds of velocity is 0. So on our velocity time graph, that means we have a line on the 0 meters per second for the first 3 seconds. Our 2 meters per second line is horizontal between 3 seconds and 6 seconds, and our negative 1 meter per second line is another horizontal line between 6 seconds and 10 seconds. We can connect our horizontal velocity lines on our velocity time graph either with a solid lines, solid vertical lines, or dotted vertical lines. This graph has 4 different velocities, and so this is your job now to identify what the velocities are, choose your scale for your velocity time graph, and graph it so that we can see what the velocity time graph would look like for this position time graph. Our first attempt at plotting a velocity time graph from our position time graph gives us this one. So the first 2 seconds at negative 2 meters per second. Second 2 meters from time equals 2 seconds to time equals 4 seconds at negative 0.5 meters per second. Our third one at 0, and our fourth time segment at negative 2 meters per second again. Putting in the dotted vertical lines, let's check to make sure this is correct. So we have a negative slope, negative 2 meters per second makes sense. Our second slope, though, is positive. So instead of negative 0.5, let's make that a positive 0.5 meters per second. Third slope, our zero horizontal line, gives us a zero velocity. And our fourth slope, again, is negative 2, so it's negative 2 meters per second. So now our graph looks the way it should to match that position time graph. If we look at our position time graph, pieces of information that we can get from it are the velocities of our object at different time intervals. We can identify the start position of our object, we can identify the direction of motion, and we can tell that it is traveling at a constant velocity. Our velocity time graph, we can also identify velocities, not spelled right, oops. We can identify time intervals for each segment of our object's motion. On our velocity time, we cannot identify where it starts. We have no idea. We can tell how fast it's going, we can tell how long it's going each velocity, but we have no idea where it starts. We can tell which way it's traveling. If we identify one direction as positive, the other direction as negative, we can identify direction of motion. We can also identify the fact that it's traveling at a constant velocity. Now let's switch things around. We'll start with a velocity time graph and see what we can do for drawing a position time graph. The first thing we need to do, again, is identify the velocity of each segment of motion for our object. The first one, our object is traveling at a positive 3 meters per second. The second part of travel, it's traveling at a positive 1 meter per second. The final segment, it's traveling at a negative 2 meters per second. What we do now is identify how far the object travels at each segment. For the first 4 seconds at 3 meters per second, our object travels 12 meters. We figure that out by taking its velocity, multiplying it by the time, velocity times time, and that gives us 12 meters. So the equation, velocity times time, gives us displacement. The way we figure that out from the graph is to look at the region between the velocity line and the zero line that gives us a rectangle. The shape of a rectangle is its base, 4 seconds, times its height, 3 meters per second. So it turns out the area between the velocity line and the origin on a velocity time graph will give us the displacement of our object. For our next segment of motion, we find the area of the rectangle, and that is 1 meter per second height times 3 seconds in time. So base times height here, we get a displacement of 3 meters. For our third segment, we're going to do exactly the same thing. Our forward motion is 12 meters plus 3 meters. Our motion in the opposite direction is negative 6 meters, negative because we have a negative velocity, meaning we're heading back towards the origin. So now we need to graph this on a position time graph. We know that we need to go forward 15 meters and come back towards the origin 6 meters. So we need to set our scale on the position time graph to reflect that. So the 5 that's there may need to be changed. So we have our positions labeled on our position time axis. Every tick mark is 2 meters. So now we're going to look at the graph and start at 0 because we can start wherever we want to. So 0 makes a convenient place to start. And we find that after 4 seconds we need to have gotten to 12 meters. We put a mark at 12 meters and connect it with 0, so there is our first segment of travel. Velocity of 3 meters per second is our slope, 3, and we've covered a displacement of 12 meters. We're going to do the same thing with our second segment. We travel 3 more meters in 3 seconds, so we're going to put a dot at 15 meters and connect it back with our 12 meter spot. For our final segment, we started at 15 meters, we end up at 9 meters, so we want to identify those 2 spots and connect those 2 points with a line that should give us a slope of negative 2 meters per second on our position time graph. So now we have a position time graph we've drawn from our velocity time graph. Again, it doesn't matter where we start, our line should look the same. Another graph, same idea. We have to identify the velocities first, and then we will plot those velocities and the displacements that occur on our position time graph. So our first segment, horizontal line on the velocity time graph, means we're not moving at all. Second segment shows that we're moving at 4 meters per second for 2 more seconds. On our final segment, that line is below the zero, so we're traveling at a negative 0.5 meters per second. Now we need to figure out what is our displacement for each of those segments. Again, we're going to look at the area under the curve, which means between the velocity line and the zero. I determined that we traveled no displacement the first 4 seconds, so we have a horizontal line on the zero. We're going to keep our position time axis as it is. We traveled 8 meters during the second segment, so we're going to connect 8 meters at time equals 6 to 0 at time equals 4, so we get a diagonal line with a slope of 4. In our third section, we traveled 2 meters back towards the origin, so starting at 8 meters, we end up at 6 meters. So we're going to connect 6 meters at 10 seconds with 8 meters at 6 seconds, and we get the third segment of our position time graph from this velocity time graph. Again, here's a third velocity time graph. Now it's your turn to figure out what the position time graph should be. We'll get rid of that 5 on the position time graph axis in case you need to have a different scale from what was initially indicated. So here's the scale that was determined on the position vertical axis. We're going to start at 0 and go down to negative 9 meters for the first 3 seconds. There's a 0 velocity for the next 4 seconds, so we're going to have a horizontal line at 9 meters, negative 9 meters. Our final velocity is a positive 4 meters per second, so that means we're going 12 meters. So from negative 9 forward 12 meters, we end up at positive 3 meters. And so our graph is going to look like this. Doesn't matter where we start, but the shape should be the same regardless of our starting point. We could also draw a graph starting at a positive 9 meters, going down to 0, and then up to positive 12 meters. So the shape of the graph is identical to our original graph. It's just slid up on the vertical scale to start at 9 meters rather than at 0. So again, we don't know where to start on a position time graph from a velocity time graph, but we know the shape of the graph will be the same regardless of where we start.